Well, good morning, ladies and gentlemen, and welcome to day 2 of the NACA Centenary Symposium. I think we had a great day yesterday, and I appreciate all your participation. It's great questions and some great panels, and I think we got a great lineup today as well. But we start off this morning with a keynote address by Dr. John Anderson, Curator of Aerodynamics at the Air and Space Museum here, but also the legendary aerodynamicist. Any of you who have studied aerodynamics probably have his textbook in one of its many versions on your bookshelf someplace. John's a legend in the aerodynamics world, and he's going to talk to us about the NACA in the 1930s, trailblazing the technical world of aerodynamics. So join me in welcoming John Anderson.
Well, I want to start out by thanking Bill Barry and all of those who have organized this symposium for giving me the opportunity to share a few thoughts and say a few words with you in honor of this 100th anniversary of the creation of the NACA. And before I even get started, I want to share with you, for me, the NACA was all about aeronautical engineering. The information, the technology that was created by the NACA went around the world. It was seminal in the field of aeronautical engineering, extremely important. And I wanted to emphasize that. It's all about aeronautical engineering. Also, the NACA is all about the highly qualified, intelligent, hard-working individuals who work for the NACA, who produce this seminal information that made the United States and the NACA famous worldwide. And I think that's important. I'm sort of giving them a shout out even before we start here. Also, you can, we'll start here. The ideas that I'm going to share with you, we'll wait for this to come up. Whoops. Nope. We keep on going back. Oh, hey, there's a preview, man. Look at that. Let's keep on going back. One more. There. I wanted that slide because it says the 1930s. This is the NACA in the 1930s. That's what I'm going to emphasize. And what's magic about the 1930s? But by the way, I wasn't physically present in this room yesterday, but I watched every presentation in its entirety throughout the day on the computer at home. And a number of the speakers emphasized the importance of the 1930s. The 1930s was the period of what we call the design revolution. That's when the nature and the configuration, all aspects of the airplane changed due to major technical innovations, major technical discoveries, a lot of which were carried out by the NACA. 1930s, before I go any further, I want to share with you two quotes that bracket the 1930s, first at the beginning and then at the end. And these quotes are, and he'll come up here in a few seconds, this man, that's Edward P. Warner. Now, Warner's name was mentioned yesterday several times. Debbie Douglas, for example, in her presentation, brought forth some of the contributions of Ed Warner. But Ed Warner was graduated with honors with a BA in mathematics from Harvard, went to MIT, and the next year graduated with a BS in mechanical engineering, and then the next year an MA. He, after that, immediately took a job with the NACA Langley Memorial Aeronautical Laboratory, and you were told this yesterday, where he was the chief physicist, and he took charge of the aerodynamics program. He helped to design and construct the first wind tunnel at Langley. You saw some pictures of that yesterday, albeit it was basically a copy of a wind tunnel at the National Physical Laboratory. And then in 1920, he went back to MIT, becoming an associate professor of aeronautical engineering. And he was there for 6 years. In 1926, he took the job as Assistant Secretary of the Navy for Aeronautics. And then in 1957, he became president of the ICAO, the International Congress of actually it's called the International Civil Aviation Organization, the ICAO. Ed Warner was a mover and shaker in the first half of the century in aeronautics in this country. And I'm going to share with you two quotes. One that was in a book that he wrote. It was titled Airplane Design, Aerodynamics, published by McGraw-Hill, 1927. And in this textbook, Ed Warner says the following, and this is sort of before the 1930s. The pioneers of aircraft design traveled in a wilderness, dependent upon their own resources at every step. No path was marked for them, and the illumination along the way was only such as they themselves might provide. Of research, in its application to aeronautical engineering, there had been hardly even a beginning, and its place had often to be supplied by inspiration, intuition, or empiricism, or go unsupplied. And then, now that's sort of really describing the woeful state of the art, particularly at the end of World War I and up into part of the 20s. And then Warner goes on in the same paragraph. The student who embarks upon aeronautical studies in 1927 is subject in some degree to a contrary embarrassment. Experimental data inundate him. The underbrush of obscurity has been cleared away. The field is even more brightly illuminated by the fruits of governmental, institutional, and private research. But listen to this. Yet, the very uniformity with which enlightenment is being cast over the subject in its several parts may prove confusing, leaving the exact course to be followed still in doubt. That was 1927. Now, on the other side of that, we have Ed Warner in a new book. It's entitled Airplane Design Performance, published by McGraw-Hill in 1936. And here is the other side of that period. Quote, all this refinement, what refinement? Well, we'll see. All this refinement becomes increasingly more important, and engineers become increasingly excellent in their demands for it, for two reasons. First, because as design becomes increasingly an exact science, and as designers are required to subject themselves to ever closer specifications and advanced guarantees for their product's performance. Errors of 5 or 10% in aerodynamic data that might once have seemed too small to notice come to assume nightmare proportions. So that's a big change. Now we have airplane designers getting uptight because the data is only 5% accurate. What has changed? One of the major things that has changed in between these two quotes is all the work that had been carried out by the NACA at the Langley Memorial Laboratory, their technical contributions. And so I'm going to share with you only 3 categories of those contributions. One is going to be the airfoil work carried out at Langley. And the second one is going to be the development of the NACA cowling. We'll say something about that. And then finally, shedding some light on the intellectual understanding of what was called the compressibility problem for high-speed flight. And Debbie, who just walked in, you recognize that guy up there. I was just quoting him as you were coming in. Okay, let's start. Let's start with airfoils. And, you know, the NACA right away when it was created recognized the almost ad hoc state-of-the-art of airfoil design. In 1920, some engineers at the NACA collected and categorized and compiled airfoil data for hundreds of different airfoils around the world. Now, what I'm showing you just one of these from this 1920 is an NACA TR-93. This is lift drag moment data versus angle attack for the Göttingen 298 airfoil that was used for the Fokker DR-1. And there are hundreds of these graphs that the NACA compiled just so that people could see, this is the state of the art of airfoil knowledge, airfoil design, and it was a mess. It was a mess. Now, during the 1920s, a person by the name of Virginius Clark. Now, Clark, this is a group photo. Colonel Clark is the man standing on the right in the back. And as a matter of fact, Clark was a distinguished graduate of the Naval Academy in 1907. He went to San Diego, he learned to fly for the Navy, and then later on became part of the Army. During World War I, he became the commander of the Army Research Center at McCook Field. That was mentioned every once in a while yesterday. So there he is on the right. Now, what's important about Virginius Clark? He designed airfoils, a whole series of airfoils called Clark, for most famous being the Clark Y airfoil. By the way, this photograph, Clark was sent to MIT for one of the first classes in aeronautical engineering. I think it was I think the date on this photograph is 1918. Somewhere in the back, I think, is Hunsaker. Nevertheless, Clark designed the Clark Y airfoil. I'm going to put that on. And here's what Clark had to say about this airfoil, about the whole status of airfoil design. And this really shows the ad hoc nature of airfoil design. This was a quote. It was published in an interview that he had with Aviation Magazine. Now, that was a forerunner of what we call Aviation Week today. It was in October 1927. Colonel Clark was asked, how do you go about designing these airfoils of yours? They've become famous by that time because so many airplanes were using the Clark series of airfoils. Now, Colonel Clark, how do you go about designing these airfoils of yours? What is the secret? Clark laughed and replied, I would gladly tell you the secret if I knew of any. The airfoil sections just seem to lay themselves out, and when good luck attends, fair results are obtained. When good luck attends, fair results are obtained. That was the status of airfoil design and development, and even up towards the beginning of the 1930s. Now, in 1920, I should say, if you just go out the hall and look down in the Milestones of Light gallery, you see, not hanging there, but on the floor now, the Spirit of St. Louis. The Spirit of St. Louis uses a Clark Y airfoil, for example. Okay. This person walked in the front gates of Langley Memorial Aeronautical Laboratory a year after he had graduated from University of California at Berkeley with a bachelor's degree in mechanical engineering. This is Eastman Jacobs. His name was mentioned several times in some presentations yesterday. Now, Jacobs, within a few years, became director of the variable density wind tunnel. Dick Hallion said some interesting things about the variable density wind tunnel yesterday. And in that tunnel, there it is, there's the variable density wind tunnel. And let me remind you, what that is a big pressure tank. And inside that pressure tank is a wind tunnel, complete wind tunnel inside that pressure tank. And that tank was pressurized to 20 atmospheres. So that means that the air pressure in the airstream flowing over the model in that wind tunnel was at 20 atmospheres, high density air. And that, in aerodynamics parlance, that means the Reynolds number was high. The Reynolds number was almost equivalent to that encountered in free flight. And so measurements, aerodynamic measurements carried out in this variable density tunnel were reasonable representations of what you could experience in full-scale flight, particularly in those days. So here we have Eastman Jacobs running that tunnel now, and he begins a whole series of in really organized, intelligent airfoil designs. Now, this is what was, if I had a laser pointer, I'd have a little red dot there, but if you look at the bottom picture, that's an airfoil, and you'll see that there's a curved line midway in the middle of that airfoil. That's called the mean camber line. It has a curved shape. That airfoil is designed by first coming up with the camber line and then wrapping around it a symmetrical thickness distribution. And that picture up on the top is the symmetrical thickness distribution. So you combine the camber line with that thickness distribution, and presto, you've got an airfoil. And you have an airfoil that is sort of designed in a systematic way. This led to a whole series of airfoils, which was called the NACA 4-digit airfoil series, which will come up here in a minute. And there they are. These airfoils, not only were they systematically designed, they were effective airfoils. The NACA tested them extensively, so there was a lot of experimental data available to airplane designers on these airfoils. And so a very large number of airplanes during the 1930s used the NACA 4-digit airfoil series. For example, not only just in the United States, but when R.J. Mitchell was designing the Spitfire, that airplane uses an NACA 2213. It's a 13% thick airfoil. At the root, tapers to a 2205, 5% thick at the tip. The Spitfire used an NACA 4-digit airfoil. Its major protagonist in the Battle of Britain, the Messerschmitt 109, also used an NACA airfoil. It was sort of a strange one. It was essentially called a 2R,12 airfoil. Now you're gonna, if you look for data for that airfoil, it's hard to find because the NACA felt that was not a very good airfoil. Very quickly after testing, they found that that airfoil, it had low drag, that was a big advantage, but also had a low maximum lift coefficient and prematurely stalled. So the NACA recommended that, here in the United States, recommended people don't use it. The engineers, the designers of the ME-109 like that low drag feature, and they use that airfoil on the 109. So, I mean, it's just an example of how the airfoil work carried out by the NACA, by people like Eastman Jacobs and his colleagues, provided a major change, a major improvement in our understanding basically of airfoil performance, and giving airplane designers the opportunity to use effective airfoils on their airplanes. This is one of the big deals during the 1930s from the NACA. Well, Jacobs didn't stop there. And I'm waiting for the next one to come up. I should say, Jacobs had a colleague at Langley, Theodore Theodorson. Theodorson in the 1930s was the most respected theoretical aerodynamicist for the NACA. And Theodorson, in parallel with these airfoil measurements being carried out in the variable density tunnel, came up with a theoretical method for calculating the pressure distributions over airfoils of arbitrary shapes and arbitrary thickness. That was a big improvement. And it was, I'll show you one of his results. This is a result actually on a Clark Y airfoil, showing pressure distributions over the bottom and the top of the airfoil. And there are two curves shown there. One is the theoretical measurement, the calculation of the pressure, and one is the experimental measurement of the pressure distribution. And you'll see that especially over the top, the lower pressures are plotted on the upper part of that graph. And you'll see there's a little bit of discrepancy there. Now, to give you some idea of the kind of person Theodorson was, he looked at that and he said, the trouble is with the experimental measurements. The experimentalists ought to take another look. Yeah, in my experience, all beginning, right from the start, even when I was educated in engineering, you always accepted experimental data as the major aspect, the major thing to believe, and any theoretical calculations, if there was disagreement about that, you would suspect the theoretical calculation, but not Theodorson. But I just wanted to throw this in, that at the same time that these airfoil measurements were being made, the NACA had their most expert theoretician working on calculating particularly the pressure distributions over airfoils of arbitrary shape. One last aspect of this airfoil design. Eastman Jacobs toured Europe in 1935. He was over there for the Volta conference, which was mentioned yesterday, and I'm going to talk about that later on. But he was there, and he took the opportunity over a space of a couple of months to tour various laboratories, including in Britain. He visited Cambridge University, and he talked with G.I. Taylor, who was a very noted fluid dynamicist, and Melville Jones, who was a very noted aerodynamicist, both at Cambridge. And they both told Jacobs that, look, we have discovered at Cambridge, in the wind tunnel, that if you have a body, whereas the flow flows over the body, the pressure keeps going down over the surface of the body as you flow down the surface of the body. Pressure goes down. It's called a favorable pressure gradient. The boundary layer on that surface will tend to remain laminar. And only when that pressure starts going up do you have a transition to a turbulent boundary layer. Now, that's important because the skin friction for a laminar boundary layer is much lower than the skin friction for a turbulent boundary layer, everything else being equal, factor of 10 lower can be. And so therefore, this was a pretty important piece of information that Eastman Jacobs took back to Langley with him. And then he sat down and said, how in the world can I design an airfoil shape to create a long region, a wide swath of favorable pressure gradient, decreasing pressure over the surface of the airfoil to encourage a large region of laminar flow over the airfoil and therefore have a much lower skin friction coefficient. Well, that was not easy. There was no way of doing that. And so Jacobs took some of the work that Theodorson had done. Theodorson said this is impossible. You can't take a pressure distribution and design an airfoil that's going to give you that pressure distribution. Jacobs went home for 3 days, studied Theodorson's theory, came up with a technique for designing an airfoil that indeed would create a given pressure distribution. Whoops, I'm going to go back. And what you see there in the top graph is a standard NACA airfoil, and you see the pressure distribution. It starts at the front of the airfoil, and it drops like a rock, reaches a minimum just downstream the leading edge, and then you have this big region of increasing pressure, the adverse pressure gradient. That encourages turbulent flow, and that was what was encountered over all these standard airfoils. Basically, they had turbulent boundary layers on them. The bottom graph is a different shaped airfoil, and you can see the pressure distribution there. It drops like a rock, or going around the leading edge. It then maintains a decreasing favorable pressure gradient practically to further downstream than the midpoint of the airfoil, and then you get your pressure increase. That airfoil experienced a large region of laminar flow and therefore had a much lower skin friction coefficient. That airfoil was called a laminar flow airfoil. There was a whole series of NACA laminar flow airfoils that were designed and investigated and measured, total measurements made towards the end of the 1930s. And that work, unlike almost all the previous work at the NACA, that work on the laminar flow airfoil was considered to be so important that it was immediately classified. And so the word didn't get around very much about these new laminar flow airfoils. But it did get to Edgar Smoot, who was designing the P-51 at North American. And Smoot had an opportunity. First, he had designed using P-51 using a standard airfoil. And then he was visited by several NACA engineers one day. This is what the NACA did. They sent people out and they talked to important people in industry. And Smoot learned about this classified laminar flow airfoil. He designed a different wing. He took 2 models up to a wind tunnel at the University of Washington, tested standard wing and tested the wing with the laminar flow airfoil. The laminar flow airfoil performed much better. Presto, the P-51 is the first airplane in history, first production line airplane in history to use a laminar flow airfoil. Now, so this was a big deal. It's an important development. Just another follow-on of the kind of airfoil work and the contributions being made by the NACA in aerodynamics in the 1930s. Now, the rest of that story, by the way, is that in real life, the laminar flow airfoil didn't really produce much laminar flow because in the wind tunnel, the variable density tunnel and other wind tunnels at Langley, the wing models were like finely polished jewels, nice and smooth. In reality, when you build something like the P-51, you have manufacturing irregularities. You have the airplane flying through the air, encountering all kinds of insects, bug spots on the surface. All of that produces roughness, which encourages the turbulent boundary layers. So for all practical purposes, that laminar flow wing on the P-51 did not create laminar flow. But, and here's a case of serendipity in the history of technology. It turned out that that shape of the laminar flow airfoil also had what we call a higher critical Mach number. That wing, that airplane could fly faster before encountering some adverse compressibility effects, which I'm going to share with you in just a few minutes. But that was the deal. That was all this airfoil work culminating in the laminar flow airfoil. Even Kelly Johnson, when he designed the P-80 in 1944, used a laminar flow airfoil. So that was very important. Okay, that's it. The airfoil work being done at the NACA, the Langley Memorial Laboratory, was very important. I'm going to quickly go to the next subject. The next subject is the NACA cowling. Fred Weick took over a new facility in 1928 at Langley. It was discussed yesterday. Jeremy Kinney mentioned it several times, the Propeller Research Tunnel. And in that tunnel, a new project was initiated. And this project was initiated really as a result of a meeting of the aircraft manufacturers at Langley. They encouraged some work on cowlings. And you'll find in the 1927 NAC annual report the following quote: "One of the problems suggested, the study of the effect of cowling and fuselage shape on the resistance and cooling characteristics of air-cooled engines was promptly incorporated in the committee's research program." And so there you have Fred Weick in the propeller research tunnel. See the fuselage, and there's one of the cowlings they were testing on the fuselage in that PRT. And the result of that work produced something that was called the number 10 NACA cowling. There's the Lockheed Vega, one of the first airplanes to incorporate the cowling. That's that circular metal area that's wrapped around the engine, the cylinders of the engine. And the NACA cowling not only reduced the drag, but also improved the cooling of the radial engine as well. And here it is on the Lockheed Vega. The Lockheed Vega, before the cowling, had a top speed of 165 miles an hour. After the cowling was added, 190 miles an hour as a top speed. That was dramatic. Again, another feather in the cap in the aerodynamic developments of the NACA at the Langley Memorial Laboratory. And the final feather in the cap has to do with high-speed compressibility problems. We'll start here. In 1918, at McCook Field in Dayton, Ohio, the Army put together a new wind tunnel. Dick Hallian mentioned that wind tunnel yesterday. In fact, he even mentioned, quite properly, it's a pretty long wind tunnel. It's 18 feet. It's a 14-inch test section. It's so historic that it belongs to the Museum of the Air Force in Dayton, Ohio, on display the last time I was there, sort of tucked in a corner. But that wind tunnel, you'll see here, that wind tunnel had speeds from 25 to 465 miles an hour. Now, what airplane in 1918 would fly at 465 miles an hour? Oh, obviously none. And there was nobody in that period of time who was even thinking about airplane speeds like that. But they knew that the tip speeds of propellers in fact, exceeded that velocity. And there were some really strange things happening when tip speeds got up close to propellers got up close to the speed of sound. And these guys, Frank Caldwell and Elisha Fales, in that wind tunnel were the first to measure the effect of high speeds on lift. Prior to that, ballisticians knew that on projectiles, if you fly up near the speed of sound, suddenly there's a big increase in drag on the projectile. But nobody had paid any attention to lift. Here's a strange-looking graph, as soon as it comes up, from this result at McCook Field. What you see there on the vertical axis is something called lift coefficient. On the horizontal axis is velocity, speed, measured in the wind tunnel. And you can see, just pay attention to the right-hand side of that picture. You'll see that as the velocity increases, all of a sudden the lift falls off the cliff. It just dramatically decreases. An important observation. They didn't have a clue as to what was causing it, but it was an important observation. A few years later, oh, by the way, I should say, this work is published in an NACA TR because the NACA funded this work at McCook Field. Okay? A few years later, in the early 1920s, the NACA gave a contract to the National Bureau of Standards in a series of tests, one of which was carried out, one series carried out at the Edgewood Arsenal up here in Maryland. Some measurements were made on airfoils. Whoops, not that guy. Well, yes. Measurements were made. Actually, they were made by Hugh Dryden and Frank Caldwell. You've heard Frank Caldwell's name when Jeremy yesterday talked about variable pitch propellers. And in the National Bureau of Standards, those guys measured, for example, a pressure distribution on the surface of an airfoil when it was going through this period where the lift coefficient is dropping off the cliff. And that was being called now the critical speed when the lift coefficient dropped off the cliff. Later on, we would call that at a critical Mach number. And the NBS results showed pressure distribution that were rather strange. You had your decreasing pressure as the flow expanded over the top surface of the airfoil. Suddenly there was a jump in pressure, and then a plateau, a flat pressure, a plateau in the pressure distribution. Now, it was known at that time that that was the kind of pressure distribution encountered on an airplane wing when the airplane was at high angle attack and the wing stalls. And that was a clear indication of stalling with a flow separating off the top surface of the wing. At NBS, these guys were seeing the same phenomena on an airfoil at 0 degrees angle attack, but it was happening at high speeds. And they interpreted, this very bad effect that you see there, the lift coefficient falling off the cliff, it began to be called the adverse compressibility effects due to a compressibility burble, they call it. That is associated with separated flow. But again, nobody had a clue why was the flow separating. Here you had a wing, an airfoil at 0 degrees angle of attack, and the flow is separating at these high speeds. What was going on? Well, John Stack, 1928 graduate of aeronautical engineering at MIT, walked through the doors of the Langley Memorial Aeronautical Laboratory. He soon became involved in a small high-speed wind tunnel at Langley. And Stack measured in 1934, for the first time, really definitive, the typical NACA kind of definitive measurements of lift coefficient and drag coefficient and moment coefficient as a function of velocity. And this happened to be a Clark Y airfoil, believe it or not. And it was absolute proof of these adverse compressibility effects, because the lift, as you see it dropping off when you get to high speed, the drag is going up out of sight. That's the kind of data that gave rise to the myth of the sound barrier, because you look at that data and you say, man, we're never going to be able to fly faster than the speed of sound because the drag is going out of sight. And they knew at that time it was due to flow separation. But what was causing the flow to separate? Now I'm going to pass by. This is one of John Stack, at this period of time, theorized, because they couldn't measure things properly at Mach 1 in a wind tunnel, that the only way we could do that is with a real research airplane. In 1934, he really was the first person to suggest a research airplane to probe this mysterious range around Mach 1, and it didn't get anywhere. That's a graph, for those of you who have studied airplane performance, that's called the power required curve, power required versus velocity. Two curves, one with compressibility, one without compressibility. Only reason I'm showing this, I found this graph in the John Stack archives at Langley, and it was in a manila folder in between some of John Stack's old IRS forms. And there's even a rusty paperclip mark on the top of that graph. But he was thinking about these things. He even published a paper in the Journal of Aeronautical Sciences about this. But John Stack, the really big contribution came. And when, in 1934, working for Eastman Jacobs was his boss, Jacobs suggested, since we don't know what's going on in this flow, why don't we put a Schlern system across the wind tunnel at these high speeds and take a picture and see what is going on in the flow? They did that, and what you see there in 1934 is the first ever visualization of shock waves occurring. The flow is going from left to right over that airfoil. There's a shock wave off the top, there's a shock wave off the bottom. First ever that aerodynamicists had ever seen that. And here, this historic photograph is being taken by these dedicated, intelligent engineers and scientists at NACA Langley. This explained the cause of the separated flow. The shock waves were separating the boundary layer. Flow separation resulted in higher drag, lower lift. That was the explanation. That was a major intellectual breakthrough in the understanding of the high-speed compressibility problem. And I don't think the NACA gets enough credit for that. Now, in part, let me quote, then this photograph, I have two quotes to share with you. When this measurement was made, here's a quote from John Becker, who became a leading aerodynamicist at Langley later on. He says, the first tests were made on a circular cylinder, not an airfoil, but a circular cylinder about a ½ inch in diameter, and the results were spectacular in spite of the poor quality of the optics. The optics, they use celluloid for the windows across the wind tunnel test section. So and those of you who've ever dealt with a Schlern system, that sounds like heresy. You need high quality optical windows. Here's celluloid being used. It was the beginning. shock waves and attendant flow separations were seen for the first time, starting at subsonic stream speeds of about 6/10 times the speed of sound. Visitors from all over the laboratory, from engineer in charge, HGE, Reed, on down. Engineer in charge. Yesterday it was mentioned when Jim Hansen was here, one of his first books is a history of the Langley Memorial Aeronautical Laboratory. The title is Engineer in Charge, and it's a double entendre because engineer in charge was what the director of the lab was called, and all these dedicated, intelligent, motivated engineers and scientists were themselves in charge of the work that they were doing. They had the professional freedom to do that, and that was important. Anyway, I diverge on that. Reed came on down, came to view the phenomena. Langley's ranking theorist, Theodore Theodorson, we saw him earlier, viewed the results skeptically, proclaiming that since the stream flow was subsonic, what appeared to be shock waves was an optical illusion, an error in judgment which he was never allowed to forget. So sometimes, everybody makes a misinterpretation. Finally, this work, the NACA didn't sit on this. 1 year later, Eastman Jacobs reported on this at the 5th Volta Conference for high-speed flight in Rome. This conference was mentioned yesterday. In fact, I think Dick Hallion mentioned it because that's where Adolf Bussmann first suggested the idea of swept wings. And also at that conference, not so well known is the following, that Jacobs gave a paper on this work at the Volta Conference. And in that paper, in keeping with the NACA's penchant for perfection, especially in his publications, that was another thing mentioned yesterday, the quality of the NACA TRs. They strive for perfection. So in keeping with this penchant for perfection, Jacobs apologized for the quality of the photographs, a fault that detracted little from their technical and historical importance. Unfortunately, the photographs were injured. This is Jacobs going on. Unfortunately, the photographs were injured by the presence of bent celluloid windows forming the tunnel walls through which the light passed. The pictures nevertheless give this is so laid back. The pictures nevertheless give fundamental information in regard to the nature of the flow associated with the compressibility burble. That was an intellectual breakthrough in my mind, which was of first order. And with that, the NACA high-speed research program was not simply on the map, it was leading the pack. So this is, finally, this kind of understanding ultimately helped us and led to the necessary information for the Bell engineers to properly design the X-1, which you heard about yesterday, and which is, of course, hanging in the Milestones of Flight gallery here. Final comment on my own. I want to wrap this up with the following. And I'm going to read this to make sure I get all the words in. During the 1930s, no other research establishment worldwide, and that includes laboratories in Britain, Prandtl's laboratory in Germany, the labs in France, etc. No other research establishment worldwide contributed more to the advancement of aerodynamics as applied to the airplane than did the NACA. Why did Messerschmitt use an NACA airfoil? The Germans did not have any integrated logical airfoil program. They used the NACA data. The engineers and scientists at the Langley Memorial Aerodynamic Laboratory were among the best, and I really sincerely mean that. They were among the best. And this is a legacy that today's NASA engineers and scientists can derive great pride from. And with that, I'm going to wrap up this discussion of the NACA aerodynamic contributions in the 1930s and how it trailblazed our understanding of aerodynamics at that time. So I'm finished.